Hello and welcome to the, I think this is the fourth class. Am I correct? Fourth class
Yes,
Yes,
sir.
sir.
on thermodynamics. So, uh, we had almost, why almost? We had completed the first law of thermodynamics and its application to chemical and physical systems. Maybe we shall be using this for a physical change later when we study entropy today and second law today. Welcome those who are watching live from the YouTube or later in the YouTube video. We are going to have a very fascinating program session today, integrating first law with second law and apply second law in solving problems. We are also joined by Priyani. Good evening, Priyani. And let me share
Good
my
morning,
screen.
sir.
Let me share my screen. This screen. I think this is the screen. Sometimes it is, yeah. Uh, am I? Can you see my screen, guys?
Yes, sir. Yes, sir.
Yes, sir.
So we shall be taking up the second law. But we are also joined by one guy from class 12, Krishna. Welcome, Krishna. We have already finished 3 classes. And that too, in the third class, it was, I think it crossed all limits. When we crossed 2.5 hours, we are almost at the verge of making a 3-hour program, non-stop. Of course, there was this, break for 1.5, maybe 2 minutes without, pausing the record. We had a break. Uh, but don't worry, you will be reminded of everything as we proceed with the second law.
Yes, sir.
And let me just read out some of these which you are not supposed to write in my presence. It's not required also. So let me write, write, read out. What are the limitations of the first law, which led to the discovery of second law? The limitations are some reactions are possible, feasible, and some reactions are not. That could not be explained by this. This is the second point. And the first point, why all natural processes are irreversible, fast, and sometimes really cannot be reversed. And if they can be reversed, you can't get into the same state of the system and surrounding. That means the universe. All engines have efficiency less than 100%, not 100% efficient. However, you are efficient in your design of engines. When I say engines, I mean the internal combustion engines, which run on expansion and compression of gases. Chemical reactions also, many of them do not proceed towards completion. Many reactions, they go forward to some extent and then they stall, they remain virtually stopped. Although it's not a static equilibrium, it's a dynamic equilibrium that we shall take up later. That also could not be explained by first law. And also, why heat can only flow from higher temperature to lower temperature? Can it not flow from lower temperature to higher temperature? It could be possible when in a heat pump, refrigeration and the heat pump devices were discovered, then they could not answer through first law. Why? You can also milk out heat, I mean, extract heat, transfer heat from a sink which is at a lower temperature to, another. We can't call it a sink, it is a source, cold source, and transfer some heat to the hot sink, the opposite of what is a natural process. So all these could not be explained. Not all exothermic processes are spontaneous. Previously, they were thinking just like water falls from a higher level to lower level spontaneously, the chemical and physical processes, they will travel spontaneously, automatically from a higher enthalpy to lower enthalpy. That means the enthalpy change should be negative. That should be a lowering of enthalpy. That means all exothermic processes should be spontaneous. Conversely, all endothermic processes are non-spontaneous. But it was found that many endothermic processes are spontaneous. Ice melts. It is an endothermic process by absorbing the latent heat of fusion. But still it is spontaneous at temperature above 0 degrees Celsius. Salts like sodium chloride, ammonium chloride, and many others, they are spontaneously soluble completely in water. Although this process is also endothermic. Also endothermic, we shall study that this dissolution process involves two things. I think you know about it, the 11th class guys. First, breaking of the crystal, that means spending crystal lattice energy amount of energy, that is plus. And when the ions get separated and they are hydrated, you get back some energy called hydration enthalpy. This hydration energy is negative and lattice enthalpy is positive. The sum total of these two is, in majority of salt, it is positive. That sum total of these two energies is called the heat of solution, enthalpy of solution or dissolution, that is positive or endothermic in most of the salts. Still, it is happening spontaneously at room temperature. You need not have to heat. Why? The reaction, the same. Another example of ammonium chloride with barium hydroxide gives a profound cooling effect, indicating that it's a an endothermic process but happens spontaneously. Many of these could not be answered by the help of first law. So scientists thought of introducing another thermodynamic property called entropy. Then they could explain all these unexplained phenomena with the concept of entropy. Let's say, what is entropy? Just write down entropy in your copy. Just write down whatever I am saying. You write down. Others I will give you. There is no need, because in these classes we are uh, you know keen to understand the concepts and solve problems, not to write like an average student. He or she needs writing more than anything else. But here we will write, but less, and shall be solving problems more. The entropy is, write down, is the measure of disorder or chaos or randomness in a system. More the disorder, the randomness, the chaos in the system, more is the entropy of the system. Unlike the enthalpy and internal energy, which cannot be determined experimentally, the absolute enthalpy, absolute internal energy cannot. Their changes can be determined. I was reminded of one thing which I forgot to tell you. You can write down in your previous copies, which I did tell you but didn't mention, that del H, as you know, which is equal to QP, the heat absorbed or evolved at constant pressure, is measured by isobaric calorimeter. The calorimeter is fabricated in a manner that the pressure will remain constant. Isobaric calorimeter, a constant pressure calorimeter. Sometimes we call it a DSC, differential scanning calorimeter.
Sir,
Hmm.
sir, we have written this before.
Oh, then can you remind me the del U, which is equal to the heat absorbed or evolved at constant volume, is measured in which kind of
Bomb calorimeter.
yes, it is adiabatic. You can write down
Bomb.
adiabatic bomb. Have you written, Rudra?
Yes, sir.
Okay. Then Sipun, good evening, Sipun. Namaskar, Sipun. I don't know. I cannot recollect who is Sipun, but maybe he is a student. I think Sipun is a he. He is a student watching, or anyone, because of my age. Many of your teachers oh, are my erstwhile ex-students, so it's very difficult to distinguish between who is a present student and who is now a teacher. So coming back to today's program on entropy, uh, entropy is mathematically, quantitatively expressed like this: a small change in entropy ds is equal to the small heat change in a reversible manner, that is slow and infinitesimally slowly. In reality, nothing reversible happens. We may be close to reversibility. I'm taking reversibility in a classical sense, where things or the process is carried out infinitesimally slowly. Don't be confused with the reversibility in chemical reactions, where reactions can be reversed, or it can stay at certain stage and not go further. So there will be, I'm sure you can understand when I am saying reversibility in physical sense, I'm talking of extremely slow process. No friction to intrigue us or to put any problem or to change any of the thermodynamic property throughout the journey. This journey, expansion and the compression will be followed in the same track. Each step can be reversed without any change in thermodynamic property. Now, when we integrate this, yes, dq by t, not delta t. No, that is the heat capacity that we talked about. If it is QP, then it is CP. If it is QV, it is CB. We are not interested in that. We want to keep the temperature constant and we have to observe it. We mean system. Then that ratio is another property. While Q is not a state function, but dq by t or q by t, the ratio is a state function. T is a state function, but q is not a state function always. Can anyone tell me when q is a state function? In
Isocoric.
isochoric process, this is Krishna. And this occasion, let me tell you that for class 12, I will be having similar kind of program in coordination compounds, in complex compounds. And you guys, particularly I am speaking of Rudra and Omkar, you guys who have already the basic foundation in general chemistry, including the periodicity, can understand 101% of the complex compounds and its exciting features, aspects, application, including the different theories that will be discussed, including the molecular orbital theory, you can understand. But there is a little, you know, caution. Caution is it is a class 12 topic. If you learn everything from here, then in class 12 you have to revise, extensively revise, otherwise you will forget. The decision is yours. We will also study that in class 12, but I will be having such a program for the benefit of public. It will be just like thermodynamics is a fascinating chapter and I want to disseminate my experience with the public. Same I will be interested to do in complex compounds. Now back to our work. You just write down this portion. Reversible heat transfer is the net heat absorbed or evolved reversibly and infinitesimally slowly at fixed temperature. At fixed temperature. This is so. If we integrate for the entire process of heat transfer, then it will be only Q, this one. So the change in entropy capital del S is equal to the heat absorbed or evolved reversibly at the same constant temperature. So the unit, just you write down very fast. The unit will be joules per Kelvin or calories per Kelvin. And since it is a extensive property, but if you want to make it intensive, then if per mole, then also you can make it, no harm. Joules per Kelvin per mole calories per Kelvin per mole. Many of the numericals that we will solve today will be having per mole basis. So accordingly, make it intensive. If nothing is given about the quantity, then make it extensive. So usually, like enthalpy, internal energy, entropy is also uh, an extensive or extrinsic or extensive property, which is size dependent. And what is the significance of entropy? It is a measure of the unavailable energy for work. Out of the entire internal energy and enthalpy, as a matter of fact, what will not be used for the expansion compression work, it might be available for other work, but not compression. That will be known from entropy change. We will be slowly learning its importance. Measure of unavailable energy for work. When I say work, I mean mechanical work for expansion and compression. More the entropy, less is the energy available useful for work. So in a very lighter vein, I can say if you talk more and become very erratic, very random in your attitude, you can't work more. If you become silent and less chaotic, then you can work more. That is an analogy in a lighter vein, right? So more is the entropy, less is the energy available for useful work. Well, we'll see that more is the entropy change in a particular process, less is the available energy for useful work. We will be doing that. But before that, let us study in depth how we can measure the entropy and how the second law of thermodynamics has been propounded on the concept of entropy. Let us, usually the processes are irreversible. So for an ideal reversible change, the total entropy, when I say I have written total, I really have meant the universe. You can write down. Whenever you find anything important, you write down. I will not always tell you, write down this. Whenever you find anything quantitative, equation, important, you must write down because you are the beginners. Even a revisioner like Krishna can always use a paper with him, as a copy with him to write down. So it is better always. So the net change of the entropy of the universe, which is equal to the change of entropy of the system and the surrounding, should be equal to 0. This is individually 0. This is individually 0. So the entropy change of the universe is 0. But in reality, we deal with irreversible processes. When we say irreversible, we mean spontaneous processes and fast processes. They're all confusing. Fast processes, irreversible processes. So that we'll find that del S irreversible will be really greater than, uh, you know, Q irreversible by T, so that the total entropy change of the universe, that is the sum of these two, will be greater than 0. And in fact, this is the second law. This is nothing but the second law and what we call Clausius inequality. Clausius inequality, this term is applicable to many other processes also, all based on second law. Clausius is one of the one of the scientists who was instrumental in propounding the second law. So this, for any irreversible natural process, the or in an isolated system, the entropy always increases. Change in entropy is greater than zero or positive. Otherwise, a process cannot happen. Less than zero will never happen. Is equal to zero, it will happen, but it will come to the equilibrium at the midpoint. And greater than zero, it will be going till the almost till the end of the reaction, almost. There are so many interrelated things from del S. We will be finding out what is del G. From del G, I will be introducing Z, another thermodynamic property or function property, and that is also a state function after some time. So we from del S, we know del Z with the help of del H and temperature. And from del G, we know the equilibrium constant of a reaction, how far it will proceed, or it will stay just after some progress very close to the reactant side, producing a little bit of product, or to the midpoint, or towards the end. If end is 99.99% or 90%, or precise calculation of equilibrium constant, and you can corroborate through real experiment has been done, and that is the success of the thermodynamic principles. Now looking to, if Q remains constant, the heat absorbed or evolved is constant, then change in entropy is inversely proportional to temperature. Entropy change is greater at a lower temperature for the same quantity of heat absorbed or evolved. The example I can give you, supposing you go to a crowd where hundreds and thousands of people are there, and you sneeze. Achhi! And you imagine the extent of chaos that your sneezing actually has generated. Just try to visualize that. Do the same thing in an empty hall, in an empty auditorium, there is no one, and do the same sneezing. Achoo! You'll find the entire auditorium will be reverberating with your chi sound. That means the chaos, the change in entropy will be more when the temperature. This empty room and a crowd, they are analogous to low temperature and higher temperature. At low temperature, same sneezing, same quantity of heat will produce more entropy change than the same quantity of heat will produce at a higher temperature. Now, I've shown you in a diagram that entropy just measures the spontaneous dispersal of energy, or how much of energy can spread out in a process, that as a function of temperature. If more spreading happens, then the entropy is more, the order is less. Order is less, disorder is more. If the spread is minimum, it is compact, then order is more, entropy is less, disorder is less. So that is minimum entropy here. And if it is dispersed and spread out, then more the entropy, less is the amount of available work for useful purpose. We will see that. Now, let me cite a few examples where entropy change is positive, or there is an increase in entropy. When solid is converted to liquid, or liquid is converted to vapor, then there will be an increase in entropy. You know the reason. The molecules will go farther apart, and apart and apart. So the phase changes that will bring about increase in entropy. More number of gaseous components in the product side. If you find in the left side, there will be less number of gaseous components, including the coefficients in the balanced equation. And in the right side, it is more. So del N is positive. In that case, the entropy will increase and del S will be positive. Randomness will be more, disorder will be more, and hence del S is positive. Greater the size and greater the complexity of the molecule, greater is its entropy. For example, propane, 3 carbon atoms, ethane 2, methane 1. So this is the order. And these 3 have similar molar masses, but propane has 3 carbon atoms. This has 4 atoms. Argon is monoatomic. So even if the 3 have similar molar masses, very comparable molar masses, but their entropies, absolute entropies, I'm talking of here this is delta S. Here I'm talking of absolute entropies are greater. Greater is the complexity of the molecule, even if the molar masses are similar. But if the size increases, the molar masses increases, then their absolute entropy at a fixed temperature also increases. I'm talking of in this direction, increases. Their absolute entropies increases. Ammonia is 17 and helium is 2, so size is more, so the entropy is more. And most importantly, greater the mass of the sample in a fixed volume. If the volume is fixed, but you have added some more substance, then the entropy will be more, the chaos will be more. But if the mass is same, we increase the volume, then the entropy, who can tell me what happens to the entropy when you increase the volume?
Increases.
Well, you allow, these class 11 students to answer, right, Krishna? It will be better. So when you increase
Yes.
the volume, you might think that they will go farther apart. So there will be decrease in randomness or chaos. No. More space you give, more volume you offer to the same quantity of substance, its randomness will be more. So greater the volume for a given mass of gas, greater is its entropy. Now let's see some cases where entropy will decrease. Just the opposite. When a vapor is condensed to a liquid or liquid condensed to a solid. Or in a chemical process, if more number of gaseous reactants are there compared to the products, well, del N is negative. In that case, the net chaos will be lowered, decreased, so del S is negative. Here, I have categorically said that entropy decreases with the decrease in volume of gas or increase in pressure. Obviously, decrease in volume is same as increasing the pressure without changing the quantity of the gas. Now let's do this problem. Have you written down the pertinent points,
Yes,
particularly
sir.
the equations, these ones,
Yes,
guys?
sir.
Yes, sir.
Yes, sir.
Oh, Priyan, you were there. So only pertinent points, units, equations, you jot down, and the remaining you can copy if you want. After the class is over, at your free time, we can do that. Now you solve this problem. Calculate the change in entropy during melting of 1 mole of ice at 273.15 Kelvin, that is 0 degrees Celsius, where the molar heat of fusion of ice is 6 kilojoules per mole. Obviously, the temperature has to remain constant. then only we can measure per mole what will be the entropy change. So del S is equal to, Q by T. So this is del H fuse. So the molar enthalpy of fusion is 6 into 10 to the power 3 joules per mole, and the temperature is 273.15. So what is the entropy change?
21.96.
It will be positive, because when solid is converted to a liquid, the entropy increases. Ironically, in case of ice, the volume decreases. So that is nothing to do with its randomness. Ice is one of the very few examples where a liquefaction will bring about decrease in volume. So ice is lighter than water. So that doesn't mean that its entropy will decrease on liquefaction. So what is the increase in entropy? Yes,
21.96.
21.96.
21.9.
the joules per mole per Kelvin. Per mole is because it is given per mole. If you would have given 2 moles, then per mole would not have been written. Or if it is given for 2 moles and it is asking per mole, then you have to divide by 2. You know all this. Do the second one. The same way, tell us during vaporization of 1 mole of water at its boiling point 100 degrees Celsius, and the molar heat of vaporization is 40.5 kilojoules. So the increase in entropy will be 40.5 into 10 to the power 3 joules per mole, and temperature, constant temperature is this. So this will be quick. So we are having a
108.535.
Sir,
8.53.
1053.
Now next problem where you have to explain only entropy change for water liquid to water gas, I mean vapor, is 100 joules per Kelvin per mole, while for the same 1 mole for benzene liquid to vapor, it is requiring, I mean the entropy change is less. Why? What is the reason? Yes.
The presence of hydrogen bonding in water.
No. First and foremost, yes, what do you think? What Krishna says, that the randomness will be, in the vapor state. Also, there will be, you cannot completely annihilate, kill the hydrogen bonding or intermolecular forces, which is hydrogen bonding type. So in that
The
case, the
boiling
chaos will be less. Yes.
the boiling point is more in T.
Now, because the size is more, I told you the size is an important factor. It is 18 molar mass. This is 78 molar mass. So, since the size is more, if you take the size, then both the liquid state and gaseous state have the same size for benzene. So here you
Oh.
can't take size. So yes, the only answer
temperature,
that you can give is T. So T, what is the boiling point of benzene? Can we have a quick look at the boiling point of benzene to be more precise? Let me search
Sir, 80.1 degree
Well,
Celsius.
Yes, sir. 80.1 degrees Celsius.
this is 100. What? But so since it is 100 here, and this is less by 20, this is 353, for example, less by 20, but this is greater, this is smaller. So then where is the, the key factor remains on temperature or with Q, the molar heat of vaporization.
So volume.
Sir,
Yes, tell me. Yes, tell me, Rudra.
sir, due to presence of hydrogen bonding in water, there should be there we need more energy, more heat
Yeah,
to break bonds.
what
So
Krishna
maybe.
brother told is correct. Because of the presence of hydrogen bonding, the the molar heat of fusion, if you compare, it will be much greater. And it is just have a look, 40.5 kilojoules per mole. You can Google search for benzene. Benzene is a more volatile liquid, even if it is greater molar mass, but due to weak van der Waals forces, the molar heat of fusion is like vaporization. I'm talking of vaporization is less. Can we Google search what is the molar heat of vaporization of
Sir, sir, 33.9
only
kilojoule per mole.
33.9, not only, but kilojoules, right?
Yes, sir.
33, but it is 40.5. So due to that, the Q by T, even if T is little less for benzene, but the Q factor dominates, that makes the del S factor more for water, liquid to water vapor, than benzene, liquid to benzene vapor. So the factor is the del H vaporization is water is greater than benzene. And that, why? If somebody will ask why, because water has hydrogen bonding, benzene has weaker van der Waals forces, right? Now, these two are home tasks for you, which will have greater entropy. 1 mole helium gas at 10K, that means a very cold condition, 10K is very close to 0K and 1 atm pressure, or same 1 mole, quantity is same of same gas, same mole at 250 degrees Celsius and at a very low pressure, which has greater entropy. For the same quantity of the same gas, only the volume is important. More the volume, more is the entropy. So we find volume nRT by P in both the cases and declare the one having greater volume to have greater entropy. Same thing happens here. This is also nitrogen, this is also nitrogen, but the quantities are different. Even then, you have to consider their volumes. More the volume, more the entropy. You just answer this at home
Sir,
and tell me, more the volume, more the entropy. This is absolute entropy. There is no physical or chemical change happening here. So the absolute entropy will be greater if the volume of the gas will be greater. Now you have to explain to me next time that here is 2 moles, here is 3 moles, but the gas is same. So then Why do you say supposing the volume for 2 moles becomes greater than 3 moles under the other conditions? Now, obviously, same conditions are there. Therefore, 3 moles will have a greater volume. You can apply Avogadro's law under identical conditions of temperature and pressure. The volume is proportional to the number of moles or number of molecules. So definitely this will have greater. So this will have a greater entropy than this. But had it been the opposite, supposing other temperature and pressure conditions would have been given, which would have made the volume of 2 moles of nitrogen more than that of 3 moles of nitrogen. In that case, which case would have been taken into consideration? You think of and answer to me next time. Here there will be a clean, what we call open and short case. Open and short case. Here quantities are same, but here quantity is more, but conditions are same, temperature and pressure. So obviously the volume will be more, so the entropy for this will be more. But had it been the opposite, what factor you would have considered to declare that this system at this particular condition has greater net entropy? Now let us enter into the second law. Let us not, this is a thought for, a food for thought that I am giving to you, and we'll discuss later. Now, welcome those who are watching from the YouTube. What is the YouTube? Yes. Many guys are watching. The programming world is also watching. The programming world, I don't know who are you, programming world. Can you identify yourself in chat box? Okay. The second law I have already told you, the entropy of an isolated system or universe either can remain constant or increases in any process which will be happening, which we call spontaneous process or irreversible process. You can just write down one definition. There are multiple definitions. The total entropy of an isolated system either increases or remains constant in any process which is happening. You can call it any process which happens, or it never decreases. If you find theoretically, if you can calculate a del S is negative in certain process. When I say del S negative, I mean the entire universe, system and surrounding clubbed together is negative, then declare that such a event will not happen. If it is coming to 0, then it will happen, but it will come to equilibrium at the midpoint. It is greater than 0, it will a right favored process. It's a right favored, you don't know whether it will be 100%, nearly 100% complete, or it will be 60, 70. That will be decided later. How much is the entropy change? Is greater than 0, okay. Is positive, okay. But how much? That will decide the free energy change, del G, which we will study after some time. And then del G will determine the equilibrium constant. Then equilibrium constant will determine the extent of a reaction or a process. The other definition is it is impossible to convert all heat drawn from a hot source reservoir into work without transferring a part of it to the cold reservoir or sink. Just like, in first law, we found that system and surrounding both are gentlemen, ladies. A gentle woman, they are called ladies. Gentle word is only applicable for boys. If some ladies are watching this, please don't take it otherwise, because that has been the norm from very civilization started from the European culture. We say ladies means gentle woman, but maybe in a lighter vein, men are not gentle usually, so we have to address gentlemen in a lighter vein. So here also in second law, that if you are taking, human system is taking some heat from the hot body, it cannot convert all the heat into work. A part of it we can be converted to work. The more the fraction of that, greater is the efficiency, but efficiency cannot be 100%. Some part you have to throw it back to another body called the cold body or sink. It's impossible to have a 100% efficient engine. So that is the outcome of the second law. Spontaneous change takes place in a direction that leads to more disorderly dispersal of total energy in an isolated system or universe. That means entropy should increase. All these, they talk about one thing, increase in entropy of the universe. So you can write down these three cases. If the entropy of the universe is greater than 0, it's called spontaneous process, irreversible process, a right favored process, or a possible process. If it is less than 0, it is impossible process. Non-spontaneous, left favored, impossible process. We cannot say really impossible. We shall find out in chemical systems. Delta G will be coming 10 to the power -2, -5. Still, such a very poor reaction where the del S universe is less than 0, but still we are interested. क्योंकि हम लोग व्यापारी हैं जो, we are doing business. For example, in case of the synthesis of ammonia, you know, del S universe is very much less than 0, and hence we'll find its equilibrium constant K is 10 to the power nearly -5. If you are just a lay person, then you will ignore such a reaction. The formation of ammonia is negligibly small, but still we have to depend on that reaction, क्योंकि ammonia can be synthesized only by that method, the Haber's process. Nitrogen, hydrogen, nitrogen is abundantly available in air, and hydrogen can be produced cheaply by the electrolysis of water. Then you can combine them with a lot of catalysts, co-catalysts, temperature, pressure. So we'll be doing all this later. So even then the equilibrium constant is very, very small. So what we will be ignoring as impossible process in chemistry, we will not ignore anything. We'll keep everything. So now, if it is 0, then we say it is a reversible process. It will attain equilibrium at the mid position. It is a possible process. So the Clausius inequality for the second law is del S universe will be greater than 0. It is in the language of physics called a spontaneous process, or a natural process, or an irreversible process. And if it is equal to 0, then it is a reversible process, will attain equilibrium at the midpoint, mid position. This we have already done several times, right? Oleg Sahu, pranam Oleg Sahu. I think the programming world is Oleg Sahu. Namaskar. Okay. Now I'll be giving you interesting examples to demonstrate try to understand very, very mindfully. I will explain to you why melting of ice at a temperature greater than 0. Say we have an ice cube and throw it in the floor. The floor, I mean the room temperature is say 25 degrees Celsius. It will melt completely within some time. You will find no trace of ice. All will be melted into liquid water, first at 0 degree, then subsequently there will be absorption of heat from the surrounding, and it will attain equilibrium of 25 degree Celsius. But why at all there is a spontaneous melting? The process is endothermic. It absorbs heat but melts spontaneously because del S of the universe is greater than 0. Let us prove that. Say ice absorbs Q quantity of heat from the surrounding. So the entropy of ice increases, and that is plus Q by 273 because ice was at 0 degrees Celsius, right? And the surrounding temperature is definitely more, say 25 or 5 or 2 or whatever. So the surrounding loses the same quantity of heat, but the temperature is little more, maybe little more, maybe more. So this is 273 plus T. So if you add this and this, that is the net entropy change of the universe, you will find the result is positive, is greater than 0. So therefore, we can prove or we can justify the second law that why melting of ice is happening spontaneously at temperature greater than 0. But if you look to any temperature below 0, minus 5 degrees Celsius or minus 10 degrees Celsius, that you keep some thing in the deep fridge to make it remain below 0 degrees Celsius. There is no melting. We will prove theoretically that the entropy change of the universe is negative. So below 0, the surrounding has an entropy decrease of Q by 273 minus T. But ice is always 0 degrees Celsius. But environment, the deep fridge or any environment is having lower temperature. So if we add up these two, this will be negative. You can have a calculation yourself, and you are a little bit knowledgeable in maths. You can say that the sum total of these two will be negative, less than 0. So it is an impossible process. It will never ever melt in a deep fridge where the environment, where the surrounding temperature is below 0 degree. But at 0 degree, what happens when the heat, they are same for all these three cases, but the temperature is same. If the surrounding is 0 degree, ice is 0 degree, then the net change of entropy is 0. So then in that case, the ice will melt, but it will not melt all. Half mole, if you take 1 mole, half mole will melt to liquid water, half mole will remain as solid ice, and the two will remain in equilibrium as long as the surrounding temperature is 0 degrees Celsius. If you make the surrounding warmer, then del S universe will be greater than 0 and there will be melting spontaneously. I hope you understand there is no
Sir,
point in spending more time in repeating these things, right? Am I clear?
Yes,
sir,
sir.
sir,
Yes,
ଆମେ
sir.
discuss କରିଥିଲୁ ଯେ reversible process ପାଇଁ del S system ଆଉ del S surrounding individually zero ହେବ sir, କିନ୍ତୁ ଏଇ case ରେ ତ ହଉନି.
Well, what Bhaiya, bro is asking that there is some change in entropy in a system, and there is also equal change in the surrounding, the total is 0. Well, I have never told you that individually del S has to be 0 unless it will be a isolated system like a adiabatic system or a cyclic process where you claim that independently both have to be 0 for a reversible process, but irreversible process, then some of them will be 0, some of them will be greater than 0, or maybe one will be less than 0, the other one will be more than 0, so the sum total will be greater than 0 to be irreversible. You got it?
Yes, sir.
So in a non-adiabatic process, there is always a loss or gain, and vice versa. If the system gains heat, then the entropy increases. The surrounding loses, entropy decreases. If the system loses energy, it is an exothermic process, the entropy of the system decreases, the surrounding increases. But if it is a reversible process, del S net change of entropy of the universe is 0, then the system and surrounding will remain in equilibrium. I mean, the change will be half, right? Any question, guys?
No, sir.
And
No,
any
sir.
other girl or ladies watching this video, or a girl who is live present in the Zoom, Priyani, you have any question?
No, sir.
Okay, then let us write down all this before we jump into numericals. Let us write down what are the entropy changes in different processes. Now, since del S is equal to Q by T and Q is equal to minus W in chemical convention, it is plus W in physics, but minus W in chemistry. So, and W itself is minus 2.303 nRT log V2 by V1 or log P1 by P2, then minus minus becomes plus. So expansion work-wise, it is negative. But since volume increases, the entropy increases, del S is positive. Work is negative, but the entropy change is positive. So we remember this for isothermal reversible process, because I said that isothermal will be automatically coined with reversible. It is buy one get one free type. So it is V2 by V1 or P1 by P2. NR. T is गायब. कहाँ T चला गया? So T gets cancelled. So only NR रह गया, and the T that was there in the work with a negative sign, but here the sign changes. Sign changes. If the work is positive, it is a compression work, then there is a decrease in entropy because the volume decreases. So in isobaric process, I think you have written, have you?
Yes,
Yes,
sir.
sir.
If it is an isobaric
No, sir.
process,
Can you wait for a little bit?
well, yes, guys who are watching from the YouTube, please bear in mind that this program is thermodynamics for beginners. Although I am not talking anything in Odia or in Hindi or in any other or Spanish, I am concentrating on English, but that too not an Americanized English or British English. It is Indian English, but maybe you can tell that maybe 20-30% will be British. To look or to be acceptable to any guy or a girl from the English speaking world to understand what I am speaking. By chance, if it comes to your notice that something good, I say it is good, it is you to decide, is going on, and you are forced to watch, then my English will not put you in any difficulty. Although you will not be comfortable, as your accents are not same as ours, and we are not sad about it. Ours is ours, yours is yours. But if you cannot understand what we are saying, and if we cannot understand what you are saying, there lies a communication gap. Now see, in isobaric process, you have to have an integration, because you know this is the heat absorbed or evolved at constant pressure is h dh by t, and since you are going from one temperature to other temperature, you have to integrate. That means find the area bound by the graph, not the slope, not the differential coefficient. The integration from T1 to T2, and we already know that del H is equal to N Cp delta T, or dH is equal to N Cp dt. So T is a variable here, 1 by T, dt is ln T. And take the limits T to T1, then you'll find log T2 by T1 with a 2.303, otherwise it should have been ln. So this is final del S for the isobaric process is N Cp ln T2 by T1, or 2.303 N Cp log T2 by T1, and applying the Charles law, where the volume changes with temperature, pressure remaining constant, then in place of T2 by T1, you can write V2 by V1, all others remaining same. Remember, this will be using, if it is NR, then it is isothermal. And this will not be T2 by T1, it is P1 by P2. If it is V2 by V1, this is P1 by P2, because that is Boyle's law. Here it is R, not Cp. If it is Cp, then isobaric, and T2 by T1, V2 by V1, right? If you carry out an isochoric process, although there is no work done is zero, the volume change is zero, but there will be change in entropy. And that entropy can be found out by integrating, because in constant volume experiment or process, the Q absorbed or evolved is called the change in internal energy, dE by T. And in place of dE, we can write Cn Cv dt. And doing the same integration, we find it is NCb. That was NCp, it was NCb. And that is 2.303 NCV log T2 by T1, and that according to the Amonton's law or the Gay-Lussac's law, the temperature and pressure, they are directly proportional to each other, constant volume. You can write in place of T2 by T1, this is P2 by P1, right? But this is Cb, not Cp for the isobaric process. I think I should give you a bit of time, maybe 1 minute or so, maybe less, to finish the writing. I doubt whether we can enter into the concept of second law in the light of free energy change, Gibbs free energy change, which will lead us to a more refined way of looking at the second law without considering the surrounding, only analyzing the system. We can find out whether a process is spontaneous or not, or it will come to equilibrium at the midpoint. Not only that, you can also find out the equilibrium constant from that. We can also find out what is the net amount of heat that is absorbed or evolved, what part of the internal energy will be useful for non-expansion, non-compression work? I mean, you have to also look to a chemical process, look to a electrical cell where there is a potential difference, and that is not an expansion compression work. That is a non-compression, non-expansion work. How much of energy will be available for that non-compression, non-expansion work? That also can be found out precisely when we enter into the second law in a different glass. We are now looking at second law only with entropy lens, but we shall look at later in our next program. We shall look at it with another lens, that is free energy lens. Of course, entropy will be there, but universe will be out. Only system. Systems change in entropy, systems change in enthalpy, systems change in the new thermodynamic property, that is free energy. Shall be looking at that later. Now, the general expression for entropy change for any process, may it be non-adiabatic process, which we have already done, isothermal, isobaric, isochoric, these are non-adiabatic process. But when there is an adiabatic wall performed in an isolated system, adiabatic process, that also the entropy change can be found out from this general derivation. Just write down. So dq is equal to dE plus P dV. This is the first law, because this dE was here and this was here plus W, but plus W is our minus P dV. Therefore, we have brought dq to one side and minus P dV has become plus P dV. I am not in the physics world. I am still in the chemistry world, but I have made everything crystal clear. Only difference that you encounter while handling the same similar type of problem in physics. So then you divide by T throughout, divide by T throughout, divide by T, divided by T, divided by T. This T get cancelled and you get dq by T, and which is equal to ds change in entropy is equal to n Cv dt by T, nr dv by V. So if you integrate both the sides and bring the constants to the left, you are left with this del S is equal to n Cv ln T2 by T1 plus nr ln V2 by V1, with the limits T1, T2 here, with the limits V1, V2 here. We get this is the general expression for entropy change in any process. Have you written, Miss Raut?
Yes, sir. Only the last one. So Krishna, bro, are you still here?
Yes, sir.
So we'll be having another 45 minutes class up to 8:30 in India time, because I have some work today. So extending class beyond 2 hours, though I will be interested, but will be not possible today.
Sir,
Last
I will
time
be leaving in 15 minutes.
okay, you can leave.
Sir, I have physics class.
Okay, no problem. You are a guest, so nothing to worry. Okay. Done?
Yes, sir.
Yes, yes, sir.
Now, another equation for entropy change for all processes can be deduced by using first the combined gas equation. Nn get cancelled for the initial and final states. Nn get cancelled. So take the ratio V2 by V1 becomes T2 by T1 into P1 by P2. So here in place of V2 by V1, if we put this here and then slightly make an interchange, you will find another equation, another useful equation, del S is equal to NCP ln T2 by T1. This is CB, T2 by T1. This will be NCP ln T2 by T1 minus NR. Here it is V2 by V1. Here it is P2 by P1, but minus sign. Remember, they're all same. 2, 2, 1, 1. But here it is plus sign, it is minus sign. So by using the combined gas law, you can change the first equation for entropy change to the second equation. So both the two you have to remember. But you do not, because you do not know in a numerical which data are given. Temperature, pressure data are given, or temperature, volume data are given. But you might wonder, if it is isobaric process, there is no pressure data required. I will tell you that this equation will be reduced to the previous equation for isobaric, previous equation for isochoric, previous equation for isothermal. So these are the two general equations which now we shall be using for adiabatic process. Still, you might be wondering, for adiabatic process, the Q is 0, then what is the fun of finding del S? Del S is bound to be 0 when Q is equal to 0. But what about irreversible? If you do adiabatic expansion very fast, compression very fast, it is according to a physics engine concept, it is an irreversible process. So there has to be a net increase in the entropy of the universe. We have to find out where del S becomes greater than 0. Is it inside the system or outside the system? That's the beauty, a challenge that we will be meeting within a short time. Now you have written.
Yes, sir.
Now we have, you don't write, don't repeat this. Now we have two fundamental equations for entropy change. If it is isothermal, temperature remains constant. So T2 and T1, this term vanishes. So it becomes del S NR ln V2 by V1. Of course, we can make P1 by P2 by applying Boyle's law. If it is isochoric, don't write it. We've already written. Then volume remains constant. That means this term vanishes. It becomes NCV ln T2 by T1. And applying Hamilton's law, you can make it P2 by P1. But NCV, not NR. So if it will be isobaric, you have to use another, the second one. You have to make this cancelled because pressure remains constant. Then it is NCP ln T2 by T1. And applying Charles' law, you can make it V2 by V1. So all processes can be explained by these two fundamental equations. In adiabatic, everything changes. Temperature changes, volume changes, pressure changes. So for that, according to the data given, you have to use the equation. Whether temperature, volume data are given, then you use the first one. If temperature, pressure data are given, use the second one. Right? So let us apply to the adiabatic process. Have you written down? Oh, no. Adiabatic process, listen first. In reversible adiabatic operation, as I was saying, that both system and surrounding will have no entropy change, because no heat is exchanged between system and surrounding, and it's a slow process. So the net change is also 0, because these two terms will exactly cancel. These two, the one will be negative, one will be positive. Can you tell me which one will be negative for an expansion process? If it is an expansion, then T1 is greater, T2 is smaller. T2 is smaller. So this term is negative, this term volume is V2 is greater, V1 is smaller, this is positive, but their values will be exactly identical. So del S will become equal to 0. So mathematically also we can prove that these two terms, they will cancel. If it is compression, the opposite. This will be positive, that will be negative. So they will cancel, and the entropy change of the system will be 0. Hence, the entropy change of the surrounding will also be 0. That I have written down that. Just you can write down. You can write down. You can write down in your copy this one, reversible, then irreversible. So I'll give a 1-minute break to put some fuel in my vehicle, a little bit of fuel and a drinks, maybe hot drink. But don't go anywhere. And if you are watching from the YouTube, then consider whether you have subscribed to my channel or not. If not, be generous. Be generous to hit the subscribe button. And also, if you are liking what is going on, then why hesitation to hit the like button? See you in 1 minute. Hello, welcome back. Sorry for the interruption. I think I have taken adequate fuel to take up also the second law in the light of free energy. At least I can introduce today free energy and its changes. In irreversible process, since the net entropy change of the universe has to be greater than zero, we have to see whether it is for the system which is increasing in entropy or the surrounding. It's not the surrounding, because surrounding is not gaining anything. No change is happening to the surrounding, but some change is happening. Volume change is happening in case of expansion. In compression, there is a decrease in volume, but even then, you will find there is an increase in entropy. You will find just after a bit, because there is a temperature effect. The volume effect may be countered by the temperature effect. In expansion, there is increase in volume, but decrease in temperature. But in compression, there is decrease in volume, but increase in temperature. So they will mutually compensate in such a manner, del S will be positive. Del S will be greater than zero. I will find that in our real calculation. Have you written down this in above equation? The
Yes, sir.
second positive term in expansion, this will be greater, this will be smaller, because there is a decrease in temperature. So the two, although it is negative, this is positive, but numerically the positive term will supersede the negative term and del S will be positive. I am talking of expansion. In case of compression, thus the opposite thing will happen. The positive term will be the first term, that will overpower the negative volume term, and in any case del S will be positive. So any of the above equations can be used to find the entropy change in an irreversible adiabatic process. Depending on which data are given, we'll be solving problems. Now, before that, let's talk about when two ideal gases are mixed, or more than two also, then there is also entropy increases. Supposing there is a partition here, the green ones are on the left, the blue ones are on the right. The two gases are separated from each other by a partition. But when you break the partition and now allow them to diffuse, then each one will expand from a lower volume to a higher volume. Not to the vacuum, it was having another gas, so it will expand. So the net entropy randomness, the chaos will increase. And this is the formula, and I will show you how it is derived. Minus 2.303 R into number of moles of A plus log mole fraction of A, Na by Na plus Nb, plus number of moles of B into log mole fraction of B. Now, how it has come, you have to apply del S for each gas separately, because A is now occupying the entire volume. Its partial pressure has been lowered. Similarly, B has also occupying the entire volume. So if you apply the isothermal case, the entropy change in isothermal case, T gets cancelled. The final volume is VA plus VB by VA, and for this VA by VA plus VB by VB, and the net sum of these two, and if you inverse it, and if you apply the Avogadro's law, volumes are directly proportional to the number of moles at constant temperature and pressure, and then make it opposite so that a minus sign will come here. Na will go up, Nb will go up, and the Na plus Nb will come down. Then we will be arriving at this conclusion, and del S mix is equal to minus R. Here I have kept it in ln, but for practical calculation, you have to make ln into log by bringing 2.303 outside. But one thing you must remember, where I have mentioned here, if equal volumes of same gas at the same temperature and pressure, because here the partial pressure is reduced, but if the partial pressure remains the same, equal volumes are added means, then supposing there is a partition but equal volumes means equal number of moles, and you have opened the partition, they have mixed, but the state remains the same. The state remains the same, the pressure remains the same, because the two gases are same, nothing called partial pressure. So in that case, there is no change in entropy. If the two gases are different and they are mixed by opening the partition, then there is an increase in entropy, and that is known from this data. You need not have to write down the steps for the derivation, that you will do at home. But this much you have to write, because we will be solving problems. How much of entropy is increased when two different gases, not same, different gases of different moles, they mix and enjoy a particular volume. Then another is a little bit, what happens when you dissolve sucrose, sugar in water? That is a dilution. If you, supposing it was having already a concentrated solution C1, and you have added water to make it dilute, then definitely the volume increases, the entropy has to increase. So since volume is inversely proportional to concentration, V2 by V1 has been changed to C1 by C2. So you will find C1 is greater, C2 is smaller, because concentration is decreased as dilution happens. So this will give you a positive term. This is called the entropy change during dilution of a solution. Just you can write down. Right? Over?
Yes.
Yes, sir.
Now, this is the last thing before we jump onto numericals. The entropy change in adiabatic free expansion. Most of the cases you find there is a free expansion, gas expands to the vacuum. Is there any change in the entropy? We have seen that W is equal to 0 as P is equal to 0. And since it is adiabatic, Q is equal to 0, hence del E is equal to 0. So everything is 0. We know it. But if there is an increase in entropy, yes. Since adiabatic free expansion is always irreversible. Irreversible means there will be, because surrounding is totally insulated. So del S of the surrounding will be equal to 0. So whatever non-zero or greater than 0 will happen, it is only from the system side. So that, how can we find out what is del S? Since the temperature remains constant, we have to, in this case, use the rule for isothermal change. So the isothermal rule is 2.303 nR log V2 by V1. That rule will be applicable here. But although the temperature remains constant, the volume expands. So the new volume and the old volume, that will be taken just like an isothermal situation you will be using to find the entropy change. You write down this equation to find out entropy change in free expansion, adiabatic expansion. If it is isothermal also, if del E 0, Q is automatically 0. So adiabatic, isothermal, they go hand in hand in this particular free expansion case. But usually adiabatic expansions are carried out. So I have written adiabatic, but isothermal can also be written. The same conclusion can be used. Written?
Sir, free expansion रे reversible work done भी zero होगा.
Hmm?
So free
What?
expansion रे यदि
You ask me in
reversible work.
English. I authorize you to ask questions in English, please, so that others can understand what you are asking.
Sir, in reversible work done, sir, in free expansion, the reversible work done is also zero.
Now, in this case, reversibility is not possible. You can't put the gas which is already being expanded to the vacuum back to one container and leave the other container in no molecules or vacuum. So it is always irreversible, and that is associated with increase in entropy. Any other question or any related question?
No, sir. Sir, in insert it was written that in free expansion, reversible and irreversible work done zero. Sir, but it cannot be reversible because
It
it used
cannot
to
be
be.
reversible. Free expansion is cannot be reversible. It is always irreversible, right?
Yes, sir, yes, sir.
Of course, if you apply some work done and try to bring back to one container, then it is theoretically possible, just like heat pump, it can possible. But in that case, it is again so-called irreversible. I mean, process is irreversible. You can't attain the same condition, whatever the original condition was there, you can't get that. You also lose some entropy. So entropy will be produced here. In that case, if you at all apply the other way, apply some extraneous work, external work to bring about this, the compression, I mean, uh, going back to the same condition, initial condition, then also you will find there will be entropy will be produced. In any case, entropy will be produced, right?
Yes, sir.
Now, this is the end before numericals. In the cyclic process, which we shall consider in a big scale in our next program, that is the Carnot cycle or any cyclic process, if it is reversible, then system del S0, surrounding del S0, and the universe del S0. But if it is again irreversible, which is the usual case, we are not ideal guys, cannot carry out infinitesimally slowly to make it an ideal. So we have to be somewhere, we have to be irreversible fast, so that there is always an increase in entropy of the entire universe. So in case of irreversible cyclic process, the entropy of the system decreases. We'll see. And the entropy of the surrounding increases much more numerically than the decrease of entropy that happens in the system. So the net change of entropy of the surrounding is greater than zero. Hence, we can dare call this as an irreversible or spontaneous process. We shall be looking all these in our numericals. Don't worry. And when we study in an extensive manner the the, the Carnot cycle, the Carnot engine, that every internal combustion engine is based on. So we'll be doing that. Now write down this problem. Not write down, solve this problem. Look to the data and solve the problem. Now I told you that these classes that you are attending, though you are beginners, you are attending a class which you have to do a lot of things at home. You are not writing extensively as a lay, as a beginner, as a average student does in his programs, maybe in class or coachings, whatever. You are doing something very challenging. You are understanding the concept, writing only the salient points, the equations, not even the derivations, and then solving problems. And in this style of learning, you will gain more confidence than the other way. So what is the entropy change during isothermal reversible expansion of 2 moles? What equation you will be using? Del S is equal to 2.303
2.303 NR log
NR
V2 upon
log
V1.
V2 by V1 or P1 by P2 if it is. So in this case, 2 moles are, if you want to find in joules, it is 8.3 and log 10 by 5 log 2. So what is the value? In expansion, there is an increase in entropy. Log 2 is 0.301.
11.5.
Joules per Kelvin. You can't write per mole because you are finding for 2 moles. Joules per Kelvin. Look to the second one. Calculate the change in entropy when 3 moles of a monoatomic gas is heated from 300 K to 600 K at constant pressure and at constant volume. So A is isobaric. So what is the formula for isobaric when the temperature data is given? Let's tell me.
Sir,
NCP
2.303 into NCP log T2 upon T1.
So if you can say CP data is given. No, not given. So it is a monoatomic gas. What is CP?
Sir, 5 by 2 R.
5 by 2 R. 5 by 2 R.
5 by 2 R. So log 600. Sorry. Yes. 600 by 300. That means volume has expanded, so the temperature has expanded, pressure remaining constant. This is a Charles law isobaric process. So this is again log 2. So what is the final value? Those who are watching from the
Sir,
YouTube, please use your pen and paper. So you'll be solving many intricate problems. Many.
sir,
43.15.
43.15 joule per
Yes, sir.
43.15. Here also we also can't write per mole. Then coming to yes, isobaric is missing. So we'll be doing the similar calculation for an isobaric change. Isochoric. I'm so sorry. Isochoric, because at constant volume, the change is called isochoric change. So what formula you will be applying? The other answer I have not given. Never
Sir,
mind.
we'll write CB in the place of CP.
Yes, in place of
Yes, sir.
CP, we'll write CB. That's it. Because temperature will change with pressure. The volume remains constant. This is again 3 into 5 by 2 into R.
Sir, it is, sir,
Oh, this is
CB.
3 by 2. I'm so sorry. Cv is 3 by 2r. That was 5 by 2. This is 3 by 2r into same log 2. So in this case, what is the entropy change in isochoric?
25.89. So
Yes, sir.
25.89.
25.89.
Now look to the second one, where it's not an adiabatic process, it is a non-adiabatic process, but two things have been done simultaneously. What to do? A diatomic gas, 3 moles, is heated and compressed simultaneously. When it is heated, it is supposed to expand, but another guy, a mischief monger, is trying to compress it. What to do? So both heat exchange has occurred, so the temperature has risen from 300K to 400K, and the pressure has also risen from 1 bar to 5 bar. So it is
Sir,
neither an
will
isobaric process nor an isothermal process. So everything has changed. So which equation you will find?
sir, the second general equation,
Second
NCP
general
ln
equation
T2,
involving pressure
temperature
and
and pressure.
temperature. So tell me, what is that?
Sir,
2.303.
NCP ln T2 upon T1 minus NR ln P2 upon P1.
Yes, it is minus.
Yes, sir.
Do you remember? If you were supposed to find out uh, in terms of temperature and pressure, it was NCP. If you just miss out, you can have a look. The two general equations that we derived here. NCP, the second one, that relates temperature and pressure data. So NCP. Temperature volume data is NCV, then the second one is NR. So if you apply, because all the two data are known, so you can find out is equal to 2.303. N is 3 moles. Cp, since it is a diatomic gas, 7 by 2 into R, that is 8.3 log 400 by 300. And at the same time, the pressure has increased 2.303 3 to 8.3 into log 5 by 1. So what is the total? There has been a decrease, as the answer says, there has been a decrease in entropy. You check. My answer could be wrong.
So it's coming minus 17.2 joule per Kelvin.
So what about you, Rudra? Is it minus 17? So I can modify the answer.
Sir, I am getting minus 15.01.
So I would rather request Mr. Umkar to recalculate later at home, right? Umkar,
Okay,
forget
sir.
about.
Okay.
So there has been a decrease in entropy because of the two cumulative effects. Two cumulative effects.
So the process is not possible.
Why? We are finding out only for the system, only for the system, and we have not
Okay, sir.
found out
Yes, sir.
how much of heat has been received by the surrounding. Definitely surrounding would have received more heat, and in this case, because pressure is increasing, so some heat, because they are gentlemen, they must have given some in the form of heat, so there might be increase in entropy of the surrounding, and the increase numerical value might be more, so that might be a possible process. It is happening. The guy is compressing, right?
Okay, sir. Yes, sir.
So we are not, in this case, we are not finding the feasibility of the process, finding what is the del S of the system, right? Now, similar situation here, it is, you know, uh, volume change and pressure change, but it is non-adiabatic. 0.5 liter to double its volume, that means 1 liter, and 1 atmosphere. No. Temperature changes from pressure remains constant from so when temperature changes, volume changes, it is not proportionate. Had it been proportionate, we could say the pressure is remaining constant. V1 by V2 V is equal to T1 by T2. V1 by T1, V1 is how much? 0.5 by T1 is 300 is equal to V2 1 by 370. Is it correct? Or are they same? V1 by T1 is
No,
equal to
sir.
V2 by T2.
N-
That
No, sir.
means pressure is also changing. Therefore, you have to find out the general law which has both the data, volume data and temperature data. Which one?
The first general.
The first one, del S is
Yes,
equal
sir.
to, yes,
Yes, sir.
2.303 n CV log T2 by T1 plus 2.303 nr log V2 by V1. This is plus. So this 2.303 n is, you have to find out number of moles here by using PV is equal to nRT, n is equal to PV by RT. P is 1 atmosphere, V is 0.5, R is 0.82. Here let us write 0.82, 0.082 into temperature is 300 K. So you have to find out the number of moles. Otherwise we can't. Number of moles will remain the same before the change and after the change. So here we will be taking atmosphere and liter to get the number of moles. How much you got?
0.0203.
So use that 0.0203 into CV, since it is CV's value is given 12.6 log 373 by 300 plus 2.303, n is 0.0203 into r 8.3 into log 1 by 0.5, that is log 2. V2 by V1 final is 1, is 0.5. So can you find out the answer I have given is very small, plus 0.175 joules per Kelvin. How much you are getting? Priyani, are you okay?
Sir, sir,
Yes,
I am
sir.
getting zero. Sir, I am getting 0.17250.
That's fantastic. It's very close to the answer I have given. I have given 0.175, but you have. So, Mr. Omkar, oh,
It is coming
It was
0.169.
0.168.
169 is coming.
okay. Let us resolve this dispute to make it 0.17. Forget. Now come to the entropy of mixing of two different gases, nitrogen and oxygen. You know that del S mix of two gases, different gases, is what is the formula?
So minus 2.303 into R into Na log Xa plus Nb log
Yes.
X.
Number of moles is 1 mole of oxygen. So 1 into log half, log 0.5. Because this is 1, so each fraction is half. So this is 1, again 1, so log half, log 0.5. So we find out this is minus. And the ultimate answer will be plus because it is half. This will be minus, minus will be plus. This will be minus 2.303 into 8.3 into minus 0.301 minus 0.301. So this will be minus 2.303 to 8.3 into minus minus already plus this 0.602. So what will be the final one? I have given 11.5
Sir,
plus.
sir, 11.508.
Fantastic. Plus
Yes, sir.
11.5
11.0.
joules per Kelvin. That is the entropy of mixing of these two gases, different gases. Now coming to another one, which is now, to me, anything done adiabatically excites me because most of the processes are taken to be nearly adiabatic because we do everything in haste. हम लोग सब जल्दी में हैं in India. I don't know why people were going in the street in cars, in scooties, in scooters, in motorbikes, in bikes. They are always in haste, as if they are going to attend some very important, event, failing which they will lose their job or they will lose the credibility, their credibility. They are not interested to even wait for 1 second. They shout at the co-rider in front of him or her, hey, give me the way, give me the way, I will go first, I will go first. They are always in haste. Therefore in Hindi we have a saying, Indians क्यों इतने जल्दी में, सब हमेशा जल्दी में क्यों होते हैं? कुछ तो काम नहीं है, आपका प्रोडक्टिविटी इतना भी ज्यादा नहीं है. इन ग्लोबल सिनेरियो द इंडियंस they do not work that much compared to other the countries where the growth rate is more, and particularly in states like Odisha and others where most of the guys they do nothing, still they are in a haste. On the contrary, though are really are in great action, they must be cool minded, they will be very very interested to wait, give way to others, to give way to pedestrians. Here whenever a rider, bike rider, starting from bike rider to a bus rider, sees a pedestrian is struggling, even if he or she is violating the rule, is struggling to go, if at all he sees from a distance, he will stop and will say, go, and then the vehicle rider, the motorbike rider, a motor car rider will go. Here, we will cross people attempting to violate the rule. Why violate the rule? Even they are in the right rule. If we are speeding, then we don't care to stop the vehicle, brake the vehicle, and go past. And कुचल देते हैं हम मतलब Indians, I find lot of road accidents which are not found. And many guys, they die while crossing the road. Many guys, now I was telling all these things because why? Because I told that adiabatic processes that excites me very much. 100 gram of nitrogen gas. Most of the processes, they are taken are done in haste, and anything done in haste, the heat will not dissipate. It will be confined. But with time, it will be having thermal equilibrium. So even if it is non-adiabatic, we consider to be a a nearly adiabatic system for some time. 100 gram of nitrogen gas at 300 K are held by a piston under 30 atmosphere in an insulated container. The pressure is suddenly released to 10 atmosphere. That means expansion is done under 10 atmosphere in an irreversible condition. And the gas is allowed to expand adiabatically. CV is given. Calculate del S system. Calculate del S system. The hint is given, find the final temperature, then use the equation to find del S. Unless you get the final temperature, you can't use any one of the two. Both the two general equations, they need a temperature. Of course, in isothermal, that term vanishes. But for other non-adiabatic, the temperature term has to be there. Also in adiabatic, both the two terms have to be there, right? So how can you get, since it is irreversible? So tell me how you can get the final temperature. It will be definitely cooling. So how to get? Rudra? Omkar? Riyani? How to get the final temperature in an irreversible adiabatic expansion?
Sir, from PV equal to nRT.
Are you kidding me? For the first time, you are disappointing me. We have done, last time how to find temperature, the final temperature after cooling. When you expand adiabatically, there are two ways: slowly,
Sir,
reversibly. Yes.
sir,
Yes.
T1 by T2 to the power Cp equal to P1 upon P2
That
to
is
the
reversible. No, that is reversible. So that adiabatic gas laws are valid for reversible changes, but irreversible changes, how the final temperature is found out, we have done. You are forgetting. Omkar?
So by work done.
You are not able to answer it pinpointedly. We have done a question relating to that, both adiabatic irreversible, adiabatic reversible. We found that the final temperature in reversible is lower. There is more cooling in reversible because the work done is more than the irreversible work done, which is much less area bound by the small rectangle. Tell me work done. Simply by saying work done, it will not suffice. You have to tell by equating which two
Sir,
expressions you will get.
sir, NCV delta T is equal to minus P external into delta V.
Yes. Now here you faltered, Mr. Rudra. For both irreversible and reversible, NCV delta T is applicable. And for only irreversible, it is minus P external into V2 minus V1. So by this relationship, you can find out the final temperature. N is how much?
So 3.57.
30, 100 by 28 is
3.5714.
Yes,
okay.
sir.
So
3.57.
3.57 into CV it is given, it is 20.8 into final temperature you want to find out. Initial temperature is 300 and external, pressure, since it is given in atmosphere, let it be atmosphere. So minus, because it is done under constant external pressure of 10 into the volume change has happened. You can find out what is PV is equal to nRT. You can find out what is the final initial volume. You can find out V is equal to nRT 3.57 into T nR T by P. P is 30. Initial temperature is also given 300. Let us use R is equal to 0.082. No, we can't use because CB you are using joules. So we what to do? 0.20.8 joules per Kelvin. So how to handle this external pressure is we can use you can use 1 atmosphere is 1.01 3 10 to the 5 Pascal. We can use it, and then you have to make a volume that is in. So it is better to keep it as such. Let it be CV. So tell me, because we don't know it is monoatomic or diatomic, we can find out whether it is monoatomic or diatomic, but just by making 3 by 2 R into the is equal to this, or 5 by 2 R is equal to this. Approximately it will be same. There will be little 19-20 का फर्क रहता है ऐसा हमेशा. The actual one and 5 by 2, 3 by 2, 7 by 2. So tell me how to proceed with this. If you convert to meter cube, it will be 2. I mean, time consuming. If you can bring it to atmosphere, 20.8, because 1 ATM,
So,
yes,
sir, in right side we can multiply with 1.3. Then we will get that in.
yeah. Let it be, yeah, you are correct. This, let it be 20.8 joules per Kelvin. Let it be liter. This is atmosphere, and this is liter. The let us find out the initial volume first. 0.082.
Sir, it is coming 2.9488.
Yes, sir.
2.948.
9488.
So let it be 2.95 liters.
Yes, sir. Yes, sir.
So we have to find out V2. So in terms of temperature, it will be nRT by P. That is 3.57. R is 0.082. NR, this is T final by nRT by V. What nRT by P, I'm sorry, P is 10 atmosphere, minus V1 is known to be 2.95. So multiplied by 101.3, right? Because this will be coming
Yes, sir.
liter atmosphere. Right? The temperature will be there, so it will be Kelvin will be there. So, but this CV, which is in terms of joule, to convert this liter atmosphere to joule, you have to multiply by 101.3, and TF is the only unknown here. So, can you guys for me find out TF?
Yes, sir.
It was initially 300 K. It has to be less. Since it is an irreversible process, it will not be very less. Had it been irreversible, then you would have applied the adiabatic gas laws, gamma T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. But here, that adiabatic gas laws will not be applicable, and the temperature that we find will be no doubt lower than 300, but it will be greater than what would have got by using the adiabatic gas laws, using the, in the reversible expansion, in adiabatic reversible expansion. Now, guys, who are watching still in the YouTube or watching at a later time will definitely benefit from our program. We are left with, I think, 2 or 3 more programs to complete thermodynamics. And then thermochemistry is relatively easier, simple calculations. Relatively easier, it will be maybe 2 classes. So I think only 2 more classes will be required for thermodynamics. The other one will be the Gibbs Free Energy concept. And on the same program, we will be doing the cyclic Carnot cycles. And I think only in one class, 2 hours class, we will be finishing thermodynamics and then go to thermochemistry.
Sir,
Huh.
sir, I am getting 242.84.
हमें कहते हैं 2 कहते कहलो
42.8454.
I think Omkar, a cross checking is required. Riyani? Shall we take
Mine is coming different, sir.
how much?
213.
How much?
213. 213.
No,
13.
no. It cannot be so low. So we shall take the value of Mr. Rudra. Is my calculation, it is coming 255. because the number of moles I have taken is 0.292. Here you have taken 2.95. So I think according
Yes,
to
sir.
this
Yes,
number
sir.
of moles,
Yes, sir. It will be
242,
higher.
yeah, it's 200. How much you told,
Two,
Mr. Rudra?
the
Sir,
244 is coming.
242. Sir, 242.84.
84. Please, this is the Kelvin. Please check again. So once you get the final temperature, then delta S is very easy to get. That is equal to what? 2.303, tell me. And what? Into?
Sir, CP,
Because you will be
CP log.
using the temperature and pressure data. So it has to be
Yes, sir.
CP.
Yes, sir.
CP log T final
T2
by
upon
T
T1
initial minus
minus
2.303 NR log P final minus P initial. So 2.303 N is already we have found out how much?
3.57.
3.57 into CP must be 20.8 plus 8.3, right? Because CB data is given.
Yes.
We need CP. You have to add
Oh,
8.3
okay, sir.
over and above the CB data. Log this final temperature we have got 242.84 by initial temperature is 300 minus 2.303 into 3.57. R is 8.3 log final pressure is 10 and initial pressure is 30, 10 by 30. So you can calculate this and tell me what is the net change in entropy of the system. We are not considering its surrounding in any case. So I think you will do at home. I am giving my value. It will be around 1 point something. I'm getting 1.9. You will be getting something different. So I'd like to check according to your analysis. It should be different, but it will be plus. Check. So with this, we conclude today's program, and I am giving this one for homework. These two. This, let me read out. 1 mole of a monoatomic gas at 300 K in a 10-liter piston fitted cylinder is allowed to expand to 20 liter in two different ways: adiabatically, reversibly, and adiabatically, irreversibly. That we have done before against a constant pressure of 0.5. The second case. Calculate del U, which we have already done. Del system, this we have not done. Del system, del surrounding, del S surrounding, del S system, del S universe for each process. So, and this one also. This will be done by a PV diagram. You have to depict the 4 processes in a PV diagram and find the net entropy change. Finally, the gas, and determine the net work done. So work done, that is nothing to do with, but still it is a home task. I am not asking here the net entropy change, the net work done, right? And the ending was antithesis. We were all
Sir,
doing, yes.
sir, in that last question, I am getting 10 point something, 10.59.
It a 1.926 what I have told.
Sir, but I am getting 10.5.
Maybe you check. That's what I am saying. 10 point plus
Okay,
10
okay,
point.
sir. 57.
But check joules per Kelvin, but you check. Are you getting the same? But Omkar, I think you have stopped, but you check. I have said 1
Okay.
point something, he is telling 10 point something. So either my calculation is wrong or your calculation is wrong. So Omkar, you and Priyani, you have
Okay,
to
sir.
confirm me. whether it is 1 point something or 10 point something, right?
Okay, sir.
And these 2 home tasks. So see you maybe today is Friday. Today is Friday, and maybe next week, one day we shall be sitting, right?
Yes, sir.
Bye. Bye bye. Those who are watching, very goodbye. A happy, a very enjoyable weekend in US where I am staying now. The guys are so ecstatic and passionate about the weekend days. They plan to do something, to go for an outing, to do some party, and enjoy the weekend so that they will put themselves in hectic 5 days schedule. Bye bye.
Good day, sir. Thank you, sir.
ତମକୁ ମୁଁ
Pranam,
ବିଦା
sir.
କରିନି, ତମକୁ ମୁଁ ବିଦା କରିନି, କରିବି।